Good morning to everyone. Today we are going to learn something about the radioactivity. Hope all of you are familiar more or less. And this is the lady. I think she is the only one who received the Nobel Prize 2 times. And she discovered the radioactivity. So first of all, we have to learn what is radioactivity. Previously, we have learned some chemical reactions, and also we have learned the atom model, Rutherford Bohr atom model, Rutherford model, or Niels Bohr atom model, and also Dalton's atomic theory. And there we have mentioned that the atom is the smallest part, and we have seen that not only the atom, we can divide the atoms into different smallest part, different types of particles, like as electron, proton, neutron, meson, antineutrino, several others. Almost 200 particles can be obtained from different types of different types of elements or atoms. And then we have learned another thing, that for any chemical reaction, all the atoms remain same, just they reorganize. That means when we have a reaction like hydrogen and oxygen is reacting to form water, that means in the left hand side or in the reactant part, we have hydrogen and oxygen. And then in the right hand side or in the as a product, we are also getting water which consists of hydrogen and oxygen. That means no atoms are created or destroyed. We have learned from the atomic theory or Bohr's atom theory, Dalton's atom theory, whatever we have learned, that all the atoms are unchanged before and after the reaction. But nowadays we have seen that not all the atoms, we have some atoms which can be dissociated to form different types of new atom. Even we have some reactions where we can see that two or more different types of atoms are combining to give a new atom. That means what we have learned from the Dalton's atomic theory, that we have mentioned that all the elements or atoms before and after reaction is unchanged, but and also it was mentioned that atoms cannot be created or destroyed in the chemical reaction. But nowadays we can see that all the it is recording. Yes, sorry. So nowadays we have seen that different types of atoms can combine together to form a new atom, or one atom can be dissociated into several atoms. That means one of the most important idea from the Dalton's atomic theory, which has been changed and which is replaced by the idea radioactivity. That means when one atom is dissociating into several atoms, that means the identity of the original atom has been changed. And again, if we combine two or more several atoms together, then we are getting some atom having higher mass number or higher atomic number. Therefore, these types of chemical reaction are these types of reaction, not should be chemical reaction, these types of reactions are creating some new atoms which was not before. That means we'll see some examples. So radioactivity refers to the particles which are emitted from nuclei as a result of nuclear instability. Actually, some of the nucleus which has very unstable, or for a short period of time it is stable. So when these types of nucleus or the atoms are kept somewhere, and if it gets the favorable condition, then it can transform from one form to another. Therefore, we can have the radioactivity, or some new radicals are continuously generating, and that is a spontaneous emission. That means the spontaneous, I have mentioned in one of the previous lectures, the spontaneous, that means which happens without the help of any other activity. Even, or we can consider it happens without the help of any other influence. We don't need to apply energy, or we don't need to apply heat, or even we don't need to apply the force. That means a spontaneous emission, it happens by itself. You don't need to apply any other influence. Okay, then different types of radiations. What are different types of radiations? So here you can see a reaction. Actually, this is an atom with atomic mass or atomic number 92, and it has the atomic mass 238. That means how many electrons and protons and neutrons we have in this atom, we can easily find out, because this is the atomic number 92 protons, and then total proton plus neutron 238. Now, if these types of element or atom is kept in somewhere, that time this uranium can be in the periodic table. You will be able to see this uranium in the atomic number 92 and the mass number is 238. And then when these types of uranium is kept in a certain environment or certain place, then instantly it can dissociate to create a new atom along with helium. Actually, this helium, we call it alpha particle. That means the charge, that means the mass and the atomic number, whatever, this is a particle which we call alpha particle, and the symbol is represented by exactly helium. In the periodic table, what we have, this helium has two proton and two electrons, sorry, two protons and two neutrons. So this is our helium particle. So ultimately what we can see, total mass number for the uranium 238. This part, the right hand side, also has 234 plus 4. That means total mass number for the uranium, which is combined, which can be obtained from these two different elements. Actually, here we are having the thorium, which has the atomic number 90, and the helium has the atomic number 2. So ultimately we are having 92, 90 plus 2. So we are having the 92. Again, here you can see we had uranium atom, but now we are having new different atom, which is thorium and also helium. So from the Dalton's atomic theory, we have learned that from any reaction, no atom are created or destroyed. But here we can see, after the end of the reaction, there is no uranium. So at the right hand side, we have no uranium. Even in the left hand side, we don't have any thorium or helium. So we are getting completely new types of atom, and which was not present in the left hand side. So there are different types of reactions. We will learn one by one. Alpha particle, as I have mentioned, this is the alpha particle. So two protons and two neutrons. Actually, it has no electron. That means here, if we write down, actually in case of helium, what we have, anyone can have the information regarding the helium? how many protons, how many electrons we have for a helium? One. For helium, no. For helium, we have two protons, and two neutrons and two electrons, because we know number of proton, number of electron are always equal in any atom. That means I have given you one question in the previous class exam. That means all the atoms are electrically neutral. What does it mean? For helium, we have, if we do not have any charge, that means if we have the charge for helium is 0, in that case we will have helium 2 proton plus 2 electrons, and then this is the sum of neutron plus proton. So as we have 2 proton, and here we are having 2 proton plus 2 neutron, so ultimately 4. But in case of alpha particle, we have only, we do not have any electron, so we have only 2 proton and 2 neutron. That means we know protons are positively charged, is it? Protons are positively charged and electrons are negatively charged. So that we have mentioned, if we have 2 protons and 2 electrons, then this is electrically neutral. But we are mentioning for alpha particle, 2 protons and 2 neutrons, it has no electron. That means this is our alpha particle. Ultimately it has 2 proton, and we can consider this alpha particle has 2 positively charged, is it? No electron. That means if we had 2 electrons, in that case we could consider helium as electrically neutral. But as we have no electron for the helium, therefore we have only 2 proton, and protons are positively charged. So we are having the proton as a, sorry, helium as a positively charged particle. Understand? Anyone have a question why we are having this alpha particle has a positive charge? No. Please, you have to respond at least. I cannot see your face. No question. Sorry, who has given you the? I have some network problem. Yeah, network problem. I am recording the video, so you can have the information of the lecture after the lecture. So I can give you the video. That is not a big issue. But if you have some question, either you can write down in the comment box, or you can ask me directly, because this is little bit different from what we have learned previously, and I think that would be quite interesting, because nowadays we are using different types of nuclear power plant, and also some of the countries are trying to use their nuclear atom bomb and many other things. Actually, we are having in Bangladesh, we have a lot of shortage of electricity. So how we can generate electricity, we can have idea from these types of nuclear radiation or nuclear reactivity. So first, as we are going to learn about the alpha particle, and I have mentioned that alpha particle is a positively charged particle. So how it can be positively charged? Because we have mentioned that alpha particle is contains just only 2 proton and 2 neutrons. We know neutrons are chargeless. So this is, it has charge 0, and proton has positively charged. So if we have 2 protons, that means we have 2 positive charge, and then finally 2 protons plus 2 neutrons also give 2 positive charge. Therefore the alpha particle consists of 2 positive charge. So whenever you have a positive charge or negative charge, now if you apply some electric field or magnetic field, that can be deflected by the electric field. So electric field or magnetic field is kind of just influence, that means it can have, if it has a positive charge, that means electric field. If we have positive electric field, then as we have the alpha particle, this alpha particle also positively charged. So alpha particle can be deflected by the positive electric field, or alpha particle can be attracted by the negative electric field. Similarly, positive magnetic field or negative electric field, negative magnetic field. So alpha particle has the charge, as I already mentioned, alpha particle has charge, positive charge, and it can be deflected by different types of magnetic field or electric field. Nucleus of the element helium. So nucleus of the element helium, what does it mean? Nucleus of the element helium. Anyone can have idea what is the meaning of this term, nucleus of the element helium? Actually, this is the definition of alpha particle. Anyone?
It means like alpha particles come from nucleus, like alpha rays emits from nucleus of the atom.
Not really. Nucleus of the element helium. That means, as already I have mentioned here, helium has 2 proton, 2 electron, and 2 neutron. But what is in the nucleus of an helium atom? There is only 2 proton and 2 neutron. No electrons in the nucleus. So what I have mentioned here already, and also I have shown here, sorry. So in case of nucleus of an helium, if we write down, sorry, if we go for helium, in that case electrons are in the, here 1 electron, here is another electron. So nucleus, we have 2 proton, 2 neutrons. So when we define the nucleus, that means only the proton and neutron. So here that is the same thing what we have mentioned, 2 protons and 2 neutrons. That is also definition of alpha particle. And again we are defining in another way, nucleus of the element helium. So in helium we have 2 protons and 2 neutrons which exist at the center of the nucleus, and electrons are at the surrounding, which is not belongs into the nucleus. Therefore, if we consider only the nucleus of an helium atom, that is the alpha particle. Then large mass and charge. Okay, large mass and charge. That means we have 2 protons, no electrons, 2 neutrons. So it has 4 atomic mass is 4. That means, and charge 2 protons. That means it has no electron. So normally it has very high charge, 2 positive charge. That means large mass and charge. It has the mass is 4 and charge is 2 plus. Therefore, we are considering large mass and large charge. Short range. Actually, short range, that means as the particle is very heavy with high charge, therefore it cannot penetrate through some substance very large range. So if you have anything very lighter with very high velocity, and sometimes if as it has a positive charge, so it can be deflected by the positive field or negative field. If we apply positive field, positive electric field, then what will happen? It will deflect, because positive deflect each other or reflect each other, and then if we have negative, then it will attract each other. Therefore, it will not go through very long range, and as it is very heavy, so anything heavy, it cannot go through or penetrate to long range or very lot of distance. Therefore, we are considering that it can penetrate only short range. deflected by electric and magnetic field. Already mentioned, that means as we have the positive charge, so it can be deflected by the electric and magnetic field. So now we are going for the, oh my god, beta particle. So beta particle is something we have, what we had for the alpha particle we have mentioned, that is positively charged, and beta particle is negatively charged. Here we can see, you can see beta particle is negatively charged. So here we have one neutron. Neutron, that means we have no proton, no positively charged. But when this, if we go for this thorium, thorium has 90 proton, and maybe we can calculate how many neutrons we have, 234. So if we subtract 234 minus 90, 144. So we have 144 neutron for this thorium. But when we are keeping the thorium in certain environment, then it is converting palladium. So the atomic number for thorium and palladium, you can see that one of the neutron, if I consider one of the neutron from here has converted into proton. That is very interesting. That means even one neutron has converted into proton, otherwise we could not have the palladium. That means the atomic number cannot be 91, because here we had 90 and we are not applying any other particle or anything. So when the thorium is kept in certain environment, you can see that the mass number has already changed. So sorry, 234, it was 234, here we have 234. Then how it is possible? Here we had the atomic number or number of proton 90, now we are getting 91. That means total mass number remains same, but the one neutron has been converted into one proton. So we are having some radiation as a beta particle, which has been converted as a big, here we can see that 234 and 234, and we had 90 protons and 91 proton. So here we can see that one neutron has converted into one proton. So we are having this negatively charged particle which has one neutron less actually. So -1. We can see this the particle which has very it has zero mass. Is it? It has no mass, zero mass. But previously we have found for the alpha particle it has 4 mass and charge was 2, but here it has charge -1 and it has zero mass. So here we have 234, 234. So it has no mass, but it has a negative charge. Therefore, this here you can see electrons from the nuclear decay. Actually, ultimately, what we are having here, if we think that we have converted into one neutron into one proton, so what we had, how many electrons we have? In that case, here we can consider the -1 charge. -1 charge, that means actually this is a electron. Only one electron it has. No electron has, we do not consider the mass of electron in any atom. Therefore, we have only -1 charge and no mass. That is possible only for the electron. So this is the electron and electron from nuclear decay. So here this is our original reactant. When this molecule, or sorry, this atom decomposes, we are having one beta particle which is considered as a electron, and we are having one atom having one more extra proton. Okay, so negatively charged, already you have shown that this is negatively charged, light longer lengths. So if do not have any mass, then previously we have mentioned for the helium it has very high mass, so it is very difficult to penetrate very long range, but it can penetrate very long range because it has no mass. So it can penetrate if we apply certain amount of energy or certain force or pressure, whatever. In that case, this no mass substance can be transferred, or this particle can be penetrated through very long range and then deflected by electric and magnetic field. Already, as we have mentioned, that it has negative charge, so that would be deflected by any types of either positive electric field or negative electric field, or positive magnetic or negative magnetic fields. Okay, so any of you have any question regarding these two types of particle? Okay, if you don't have, then we can move forward. And also here we have actually both of them, both alpha particle and beta particle are generated by the decay of some radioactive atom. So here you can see we have a lot or very large particle, or large, sorry, not large particle, large atom, very large atom. And when this atom is dissociating, we are getting some either helium particle, or sorry, that means alpha particle or beta particle. So both of them are generated from the dissociation of highly molecular weight, sorry, highly atomic weight atom. Therefore we have mentioned that where is in previous slide we have mentioned that this is formed by the decay of radioactive material. Okay, different types of radiations. Positron. So we have mentioned in the previous slide different types of particles. So alpha particle and beta particle. Now we will be learning about different types of radiations. So here positron. So this is a positron. So it has only one proton, no neutron. So we can see that when this types of particle is, that means one positron, this positively charged beta particle. Okay, so here you can see, that means, oh sorry, this is the positron, positively charged beta particle. This is positively charged beta particle. So this is our positron. So if we have one proton, this is one proton, no neutron. So when one proton is dissociating, so one proton is converting, here you can see this is a neutron. That means one proton is dissociating to have or to create one neutron and then one positron and some energy. That means some energy which can be used for some other purpose. Later we will learn about that. So positron, positively charged beta particle. So this is our proton. So if we have this proton, then we can dissociate this proton into neutron and then one positron and high energy, this frequency. So here is our one example. This is phosphorus. One phosphorus contains 15 proton and 15 neutron. So when this phosphorus is dissociating or decomposing to create one silicon atom with the mass of 30. So here you can see the mass remains same, 30, 30. But the number of protons. Here you can see the number of protons. Previously in the phosphorus we had 15 and now we are having 14. So how many protons we are in lacking? Actually, here from here you can see one proton. Ultimately we had the mass number 30. What does it mean? That means one proton has converted into one neutron. Otherwise we could not have the mass 30. In that case we should have the mass 29, because if one proton has been left, in that case we could have one. That means the mass should be 29, but we are having the mass is 30. That means one proton from the phosphorus has been converted into one neutron. So ultimately we are having 14 protons and 16 neutrons for the silicon. 14 protons and 16 neutrons, so that we are having the mass is 30. And this is one beta particle which has no mass. Actually, one electron less. So one electron less, that means if we write down for the electron, that means efficiency of electron. If it has more electron, then we put minus charge, and we are having the plus charge. That means it could have one extra electron. So it has a deficiency of electron. So we are having one positive charge. So this is the beta particle what we are having, the positive charged, because this particle do not have electron and this is positively charged. Therefore this particle can be deflected by some electric and magnetic field. Okay, so electron capture. Here we have mentioned positron. Now electron capture, you can easily understand what is going to happen in this system. That means electron capture. Now this is a electron, and this electron will be taken by this tellurium to convert into some other particle. So electron, that means it has one electron, no proton or no neutron. So when this tellurium is taking this electron, so the mass number or atomic number will not or the electron number, sorry, we will have the electron. This is one electron, so this electron is added to this tellurium. So this, when this electron is captured by some other radioactive element, then the element is converting into, you can see the mass previously it has 202 and that number of proton it has 81, but here we are having 80 as the atomic number and this is the mass number. Mass number remains same, so that we can see that one proton has been converted into one neutron, so that we can get the same configuration. That means mass number is 202. So as we are adding one electron, that means one less, so it has one extra electron, that extra electron, and then that is helping to convert one proton into one neutron. So the atomic number is decreasing by 1 because one proton has been converted into one neutron. So we are having the mass number 1 is less and followed by X radiation. That means ultimately we will have some radiation, that means the energy. So this is the particle what we are obtaining from the tellurium. This is mercury. So when we are capturing electron, when electron is taken by the tellurium atom, it convert into mercury addition to the some radiation. Then what is gamma ray? So gamma ray, you can see nothing has been changed for this except one symbol. Anyone have the idea what does it mean, this star star?
In the excited state.
Exactly. So in the excited state, here you can see, for we have mentioned previously many times, that means anything having the excited state, that means it has more energy than the natural state. Therefore, when this extra energy is released as this particle, in that case, the total atomic number, total mass number remain same, and then just it is releasing the excess energy what is it had. So it remains the atomic level. In atomic level, it remains same, thorium 90 230, 90 230, but we are getting this is a particle or energy. In terms of energy, what was the excess energy it has? So now we can see this particle, it has no mass, no charge, is it? So if it has no mass, no charge, only the energy, that means kind of radiation. If it has the kind of radiation, then it can penetrate through large substance, or it can penetrate long distance through any substance. Therefore, we can use these types of gamma ray for different purposes. We learn one by one. So it has no charge, no mass. And in previously we have mentioned for alpha particle and beta particle, both of them has charge, but beta particle has no mass, alpha particle has mass 4. So you have to remember this term, so that why these particles can be penetrated or why which one cannot be penetrated. So you need to remember, because we have mentioned alpha particle has mass 4, which is very large mass, and then it has 2 positively charged. Therefore, it can be deflected by some other electric or magnetic field. Beta particle has no mass, so it has penetrating power high compared to alpha particle because it has no mass. But in case of gamma rays, it has neither mass nor charge. Therefore, it can penetrate even more compared to the beta particle. So if we classify based on their penetrating power, alpha particle less penetratable, or it cannot penetrate too much, and then beta particle, and then gamma particle. Okay, so we have mentioned all of them: alpha particle, beta particle, gamma particle. Now we are moving in the forward. Okay, now what we can do using these types of radioisotopes? So as already we have mentioned, we can generate huge amount of energy. If we have, here you can see, if we have some gamma rays, that means radioactive thorium. So if we can have radioactive thorium in a reservoir in excited state, this thorium can generate high energy. So if we can collect this energy, then we can transform this energy into different types of form, so that we can have the source of energy and we can transfer to different power stations or wherever we want. So these types of energy generation. Okay, so although it may present potential health hazard, radiation from radioisotopes has useful applications in fields such as medical diagnosis and treatment. Every diagnostic center, we have the X-ray machine. What we do using the X-ray machine? Anyone can have the idea what we can do for the X-ray machine? And also I have mentioned we should not take the X-ray very often. Anyone can remember? What is the yes? Yeah.
Cameras are used to take pictures of the compact tissues like bones.
Yes.
Cartilages.
Yes, then why you should not have X-ray very often?
Because the rays is not good for health. The rays are not good for health.
Yes, health hazard, but actually this is the general term for who are non-science students. But as a science student, you should have a specific reason. I have mentioned that. Yes,
the X-ray rays have a
Carcinogenic.
very high frequency. When
high
frequency is
frequency. Yes, then
when frequency is increasing, the energy also increasing. So it has
exactly.
high energy. So that energy is not good for our body when it's come.
Isn't it that
No,
exposure to
you
high
was
level radiations
Sunira.
can make carcinogen? Yeah,
Yeah,
yeah.
just let me explain her. She was almost perfect, but just remained one term, as she has mentioned that the X-ray has high frequency, and high frequency corresponds to high energy. And then if these high energy particles are passing through our body, that means through our cells, in that case these cells can be degraded or dissociated. So we should not take the X-ray very often, or our tissue, this the cell or tissue that can be damaged. So it was very good. So we should not have the X-ray very often. So we are mentioning some of the health hazard problem we can have. However, we need to have in my medical diagnosis and treatment. So we need to use the radioisotopes. Then agriculture, we can kill some germ or some insects using the radioisotope, if we can use in agriculture field. And also sometimes we can keep the seeds. If we want to store the seed for a long time, then we can apply some radioisotope, radio active particle or radioactivity or some ray, so that we can keep germ free of the seeds, so that in the next year or maybe 2 years or 3 years later we can use the same seed. But if you keep the seed, even if you put some rice in a bowl or in a bucket for maybe couple of months or 2-3 months, then you can see some of the insects has been created. But if you put some mm, spice, like as which one, I have seen some of the spice. If we put some spice inside a bag or inside a bucket of rice, then no insect is created there. That means some radiation is continuously coming out from these types of spice. So that radiation is not good for the insects. So we can have it's okay. So we have the recording, so we'll be providing the recording. Those who have the problem in the network, no problem, just when you are available, please join once again, no problem. So we can use the radioactive isotopes in different purposes: medical diagnosis and treatment, agriculture, scientific research. That means we have to use huge energy, or sometime we need to create some new particle or some other energy. So we can use different types of radioisotopes in research. Power industry, as already I have mentioned in the first, that means power industry, from any radioactive isotope we can, when the radioactive isotope is dissociated, it can form a very stable isotope of some other element. At the same time we are getting huge amount of energy, so that energy is stored and distributed to the public. So power industry uses, or we are making nuclear power plant. So that nuclear power plant actually uses these types of nuclear reaction. So they can have lot of energy from there. Determining the dates of archaeological and geological events. So if we want to have some idea when the earth was created, and also sometimes we may get some fossils, maybe under the water or somehow in the inside the mine. So we are getting some fossil, so we can get the idea what was the age for the substance. So using these types of radioisotope, we can have the information. That means carbon dating. You will remember, or you have learned the term carbon dating. So actually that is carbon 13 dating. And we in the last class we have learned about the radioactive, we have learned about the half-life. Half-life, that means how much has been reduced from the initial. For any substance, if we want to determine the age, then we can use the carbon 13 dating. So we can get the initial, that means what was the initial concentration. If we want to have, or if we want to determine the age of any substance, then we can measure the concentration of carbon, and we can have the idea if it is a first order reaction or second order reaction, whatever, because we have mentioned in the previous class. And then we have learned about the half-life. So for how many years it takes to reduce the concentration into half, or how long time it takes to reduce the concentration into half, that is our half-life. So for any substance, if we observe, if we obtain from the mine or some other sources, then we can get the half-life for a certain period, and then we can get the initial concentration, what was the initially, and then how long it took to come to this stage. So we can get the idea about the age of the substance. Then nuclear energy is generated from fissionable uranium 235. Okay, fissionable, we will learn that term little bit later. Fission and fusion, we learn these two different terms. So nuclear energy is generated from fissionable uranium 235, 7.1% of the natural uranium. Okay, so for the nuclear power plant or nuclear energy, most of the time we are using the uranium 235, and almost nowadays what we are using around 7.1% of the natural uranium what we have in the universe. So definitely that is decreasing day by day, because we are using the uranium to generate the nuclear power plant, nuclear energy. So uranium 235 can be used to get some new particle. We will see what types of particle we can have. Then fissionable plutonium 239 can be made from uranium 238, does not undergo fission. Okay, so fission and fusion will, as already have mentioned, I will teach you in the next slides. So does not undergo fission. Plutonium 238 can be used for fission reactions. So we can have 239. This plutonium can be converted into can be used for fission reactions. Okay, so mainly from this slide you have to learn what are the uses of radioisotopes. That means you have to remember these terms. So what are the terms? The medical and medical diagnosis and treatment, agriculture, scientific research, power industry, determine the dates of archaeological, geological events, and we have many more others, but we don't need to learn too many things, just try to remember some of them. Okay, what is this? Radioactive isotope. What are the isotope and which can be used for what different purpose? Cobalt 60. This is a radioactive isotope. Sometime you may be you may think that all the radioactive isotopes are very large atomic mass. Actually, that is not necessary, because to be radioactive isotope, just it need to have more neutrons or less neutrons, whatever, from the natural. That means that system or that atom exists in the nature and it is very stable. But something some atom which has very less abundance in the nature, or it has more or less number of neutron compared to the natural one, so that we can have these types of transition atom or very short-lived atom can be converted into the long life, that means more stable atom using this. So we can have, here you can see cobalt 60. That means the mass of cobalt is 60. However, that is not very large atomic mass. Here you can see thallium 201, and then uranium we have mentioned. Uranium mass has 235 or sometimes 238. So sometimes we can have very small atom with very high radioactivity. Just we have mentioned, if we go for cobalt, how many protons and how many neutrons it should have in normally cobalt. That means cobalt has the atomic number maybe 27. Just a second, I can find out. Cobalt has the cobalt. Yes, atomic number 27 and the mass number is 59. Atomic mass 59. So if the cobalt has one extra neutron, that means this cobalt 60 is radioactive isotope. So for which purpose we can use radiation therapy to prevent cancer? That is very important nowadays. So everywhere in the world there are lot of cancer patients, and when these cancer patients get the cancer, if they do not get the radioactive therapy, radiation therapy, then they die very quickly. Even in USA, the house where I lived for 1 year, the landlady, she died just after I came back to Bangladesh. After 9 or 10 months, she died due to cancer, and she got the therapy, but that was too late for her. So anyway, so to prevent cancer, actually, any of you have idea how the cancer is created or what is cancer?
It's when like two protein molecules are displaced and the growth of cells is uncontrolled. So body cells
Yes,
keep going through mitosis.
exactly. Then if we want to treat the cancer, what we need to do?
Like stop uncontrollable
Exactly.
growth of
So
cells.
we need to stop the uncontrolled growth of the tissue. So if we can select the region, that means in which part of the body we have the excessive growth for the cell or tissue, just if we can select that region, and then if we can apply this highly radioactive element, that means if we can apply the radiation, then that excessive growthable cells that can be destroyed. So if we can destroy that excess growth cell, and if we can kill, then these types of disease or cancer can be prevented. But if the cancer is spread over the whole body, then it is very dangerous, or a very large portion of the body. In that case, that means if we have a small tumor or a small cancer, or cancer in some a small part, that means at the initial stage, in that case that can be helpful. Even sometime if we can remove the part by surgery, that means if it can be diagnosed in very initial stage before spreading all over the body, then we can remove by surgery, or we can do that by the therapy. But if we have to use the therapy for all over the body, that can be very dangerous, because this therapy, that means this radiation therapy, this energy or this radiation has very high energy, therefore that will kill our normal or our body cell also. Therefore if the cancer spreads everywhere in our body, then we need to apply the therapy all over the body, and many of our body cells will be destroyed, and our body will be decomposed very soon. So we cannot survive till then. So if we can diagnose the cancer in very early stage, that can have some possibility to cure. So then what is the use of iodine 131? Locate brain tumors, monitor cardiac, liver and thyroid activity. So using iodine 131, we can diagnose the brain tumors. We can diagnose where we have the brain tumors, and also monitor cardiac, liver and thyroid activity. So we can monitor the cardiac problem or the liver or thyroid activity using the iodine 31. Carbon 14. Study metabolism changes for patients with diabetes, gut and anemia. So carbon 14, actually this isotope is quite unstable. All of them, among all radioactive isotope, that means this is very unstable. So we have to generate these types of isotope by some other reactions, or sometimes in the nature they are found in very less percentage. That means maybe 0.001 percentage, so that it is very difficult to collect that types of isotope and also store, so that these types of isotopes and these types of therapy is very expensive, because these types of isotopes are not very much available in the nature. So if we want to collect and if we want to use this, that is huge amount of money matter. So we have to spend a lot of money for this types of treatment. Then carbon 11, tacked onto glucose to monitor organs during a PET scan. That means carbon 11, if you want to monitor a fish, that means if you want to monitor a fish inside a pond, in the pond you have a lot of fishes. So if you want to monitor the activity of that fish, what is doing, what it is eating, or what types of, how far it is moving, how far below it is going down. So you have to tag. That means if you go somewhere, and even during the day of election, during the day of election, the person who go inside the election booth and who is completed the vote, that means election process, and the people, when he come out or he or she comes out, then people give one black mark in his finger or nail, so that it can be identified. That means the election process for this person is completed or done. So we are tagging on glucose. So we are changing one carbon from the glucose with carbon 11. That means naturally we have the carbon 12 in the glucose, in our body glucose. So if we change one carbon with carbon 11, that means that is called tag. So we are identifying or selecting the glucose with tagging this carbon 11. So we can monitor, tag onto glucose to monitor organs during a PET scan. So we can monitor if we want to monitor the organs for a PET scan or for other different purposes. So we can use carbon 11 for the tagging. Sodium 24, study blood circulation. So we can use sodium 24 isotope to study the blood circulation. Thallium 201, determine damage in heart tissue, detection of tumors. So there are two main uses of thallium. So we can determine the damage in heart tissue, detection of tumors, and then technetium 99. So locate brain tumors and damaged heart cells, radio tracker in medical diagnostics, imaging of organs and blood flow studies. So there are different types of uses of different radioisotope, but mainly our major use are these. But specifically, if we want to learn what are the different purposes of different radioisotope, so here you can see the specific use of different types of radioisotopes. And then radioactive isotopes, so we are going increasing by mass. Americium or americum 241 for uniform thickness when rolling steel and paper, determine location of oil wells. Okay, so first let us consider this one. For uniform thickness when rolling steel and paper, so we are making writing paper, or we are making some aluminum foil. All of you are familiar with the aluminum foil and writing paper. So the aluminum foil or any metal, if we want to make the uniform thickness, so we can measure. How we can measure this at certain, if the thickness is certain, then we can penetrate through that thickness or that much thicker wall. That means if we have one page of paper, if we have like this one page of paper, if the thickness of this paper is not is thicker, like as this is on cover, so if the page is very thick, then these types of radioactive element cannot penetrate, or the radiation from this americium 241 what we are obtaining, this radiation cannot penetrate. So in that case we need to make that thin. So whenever or wherever the thickness is very high, through that portion, that types of radiation will not be able to penetrate. So we will make the surface as thin as possible by pressing the pressure and determine location of oil wells. That is very interesting. So if you can find out some oil, so in Bangladesh we do not have too many oil or mines. That means if we can use these types of radioactive, so in America they have, actually this element was invented in America and they have given the name as americium. So they are very good in finding the wells or mines. So sometimes the American people are hired to search if we have some wells or not. So these types of radioactive isotope can be used to find out the location of wells in large area. Then sodium 24 already mentioned one. Oil studies and to locate leaks in pipelines. So if we have some leaks in pipelines, then we can find out where the leaks are. So sodium 24, this radioactive isotope can be used to find the leaks. Iridium 192, test integrity of boilers and aircraft parts. So we can use these types of iridium 192 isotope, radioactive isotope, to test the integrity of boilers and aircraft parts. Uranium 235, nuclear power plant and naval propulsion systems fuel. Okay, so nuclear power plant and naval propulsion system fuel. That means if we want to throw some rocket, that types of system, or some mainly to propulse the rocket, naval propulsion system fuel. So we are using mainly nuclear power plant and naval propulsion system fuel. Production of fluorescent glassware and colored wall tiles. Okay, colored wall tiles. That means if we want to make the different types of fluorescent glassware. So if we have some glass and continuously it will glow light, so that can be prepared by the uranium 235. So production of fluorescent glassware and colored wall tiles. If you want to have your room to decorate with very colorful tiles, then you can make the uranium 230. You can use uranium 235 radioisotope to make the colorful wall tiles. Californium 252, determine moisture content of soil, important for road construction and building industries. Actually, this is done little bit downward in the earth. So if we want to build a very big rise building, that means Burj Khalifa or Taipei 101, they have made the building 101 or 105 store. So this is very large. Normally, when they have to make the constructive idea, they have to test the soil quality. If the soil quality is very good, then they can build the high-rise building. Otherwise, and soil quality, one of the parameters for the soil quality is the amount of moisture. If the moisture is not certain or a specific range, then that types of place cannot be used to make high-rise building. Maybe very short building, maybe 1 or 2 store, that can be okay. But if you need to make the high-rise building like as 101 or 105, so that is very high, very large structure. So in that case, you have to test the soil quality thoroughly, and that need to be done by using the Californium 252. So that are the some very important uses of different types of radioactive isotopes. So try to remember as much as possible, but you don't need to memorize all of them. Hope some of you can easily remember uranium 235. All of you are familiar with this because everywhere we are discussing about the nuclear power plant. So we are using this uranium 235, and also you can remember cobalt 60. That is very good for the radiation therapy to prevent cancer. This is very important. So try to remember some of them, so that that can be if I ask you to write down some of the radioactive isotope, uses of some of the radioactive isotope, then you can write down at least 2 or 3. Okay, then carbon dating. Carbon 5600 years. Carbon 5600 years. So here what is, we can see carbon, argon, sorry, Kr, K potassium, argon 1.3 BY. Dating radioactive decay follows first order kinetics. As already I have mentioned about the half-life. if you know the half-life of any system, then you can get the idea what was the initial concentration. That means what is the, and also we need to learn the what the radioactive, that means what types of reaction it follows. If it is first order, second order, zero order, or what order. So if we know the types of the reaction, that means first of all we have to find out, maybe we have some sample, and then we are measuring the concentration of the radioactive carbon. That means carbon 13 or carbon 14 or carbon 11. So we can have, let us consider our age, we are in 2022. So if we consider the age somewhere in the 2000, now we are in 2022, we can get the monitor in 22 years before we have taken the data for the carbon what was in the sample. Then after 22 years, or even after 1 year, 2 year, 3 year, or even shorter time also, if we can do that one, that means the amount of carbon, radioactive carbon, is decreasing with time. So how much decreasing per day or per year, or that means if we can know what a small percentage has been decreased, so we can have the idea what was or how long time it takes to reduce the half. That means right now how much we have, then what was initially at the beginning of the time, that means when the reaction started. So we can get the idea of the age of the substance. So radioactive decay follows first order kinetics. So most of the time that radioactive decay follows the first order kinetics. So neither zero order, no second order. So that is very simple. So we have learned that directly the radioactive decay is proportional to the concentration of the initial concentration. That means if the initial concentration of the reactant is very high, so the decay would be very high. And then with time, the decay is decreasing because the concentration of the reactant has been changed. So that is the idea of the first order kinetics. So here we are mentioning that radioactive decay follows the first order kinetics. Therefore, we can say that the carbon, this is 1050. Okay. So carbon, we can use carbon 14 to get the idea about the half-life, and then we can have the idea what was the initial concentration and what was the exact date or what was the time initially the reaction started, or carbon 14 dating. So we can get the age of the substance. What happened? Okay. So you can see band of stability. Oh, band of stability. That means here you can see number of protons and number of neutrons. As already I have mentioned, in some radioactive reactions, either some proton is converting into neutron or some neutron is converting into proton. So how the change happens? If the change happens, here you can see one pattern. Here initially it is expected, if the number of proton, number of neutron, the ratio is 1:1. So that is expected, that should follow this pattern, because initially we have started here. So this line is expected. That means if it do not change, that means the number of proton and number of neutron, or the ratio of number of proton and number of neutron do not change with time at all, then we could expect the time for this way. So the change in the pattern should be like this way. But as the radioactive isotope, we have mentioned that the proton or neutron changing interchanging. Therefore, in that case, the ratio of proton and neutron would be changed, and then after certain period of time, it has changed the pattern and it is deviated from the expected line. So we are having this band. That means how far has been changed from this. So we are monitoring, and then from this we can have the idea, the band stability. That means how far that is expected and that is the real. So we can have the information, the how far is the band stability, or what is the band stability. Nuclear fusion. So first you can see a reaction. What is this? Or maybe we can go for here. This is a very large molecule, large atom, uranium-235. When this uranium-235 atom is attracted, or some energy or some particle is applied on this uranium-235, this is very big particle atom, then it decomposes almost equally. That means this is very large one. This large one is decomposing to multiple, more than one, and actually these fractions are quite similar, not exactly same, but you can compare. Maybe we have mentioned the uranium mass is around 90, so maybe we can expect, sorry, atomic number if it is 90, then we can expect this one can be 40, this one can be 50. So like this way, or maybe 42 and 50, 42 and 48, something like this. So comparable, but not exactly in same way that this uranium-235. Sorry, uranium-235, that means 90 is the atomic number. So we are expecting that is comparable, but not very far away. But the main idea for the nuclear fusion is we are dissociating one molecule, sorry, one atom into multiple with the help of some other particles, some energy or particle or the radiation. So we are fusion, dissociation. So you can consider this particle or this atom is dissociating into different types of particles with similar mass or similar weight. Then we are radiating some energy. When this atom is dissociating with the help of some particle, then these two or more atoms are generated, and at the same time huge amount of energy is created, and that energy can be used to do some other work, or even this energy can be used to dissociate these types of particles or even these particles. So we can have different types of, so uranium-235 nucleus. So we can have, this is, we have the initial atom, and it can be dissociated with the help of neutron or some other particle or some radiation, and then it is dissociating and it generates some excess energy, and that excess energy can be generated, sorry, that excess energy can be used to for further reaction. Here you can see that this energy is some extra neutron also can be obtained. So this neutron can further attack these types of uranium-235 atom, and successively or continuously this process continues, and simultaneously when these types of uranium-235 decomposes or fusion, then we can have lot of energy, and that energy can be used to for other purposes. So we can do some other work using these types of energy. So here you can see the nuclear fusion, sorry, not fission. So now we will have break for 10 minutes. So I want to stop the recording or pause. Okay, we have been learning the nuclear fission and fusion. Actually, the term what I have mentioned previously, little bit need to be corrected. That means fission. Fission means diffusion. You can consider just dissociation. Nuclear fission means dissociation and fusion means combination, combine. So here this is a neutron. When this neutron attacks this uranium-235, it dissociates two different atoms. That is nuclear fission. And another way we can consider, when this neutron is combining with this atom, that is called fusion. So actually, if these two different particles combine together, maybe you have learned about the fusion music. You have learned that fusion music. Fusion music is the music when some part of one music and some part of another music are combined. That is called as fusion music. And then exactly similar way, actually the fusion music term has came from this idea. That means when two or more particles are combining together, fused, when two or more particles are fused to make a new particle, that is called as fusion process. So if I show you the definition, so you can see this is fusion, is a reaction that occurs when two or more atoms combine together to form a single heavier nucleus. That means initially it has lighter particles, lighter nucleuses, two or three or more. So when two or more nucleuses combine together to form a heavier nucleus, that is called nuclear fusion. And then fission, just opposite this. When one particle or one atom decomposes into more particles or more atoms, that is called nuclear fission. Actually, in this case, we need some reactor. So reactor, actually, we can consider as an energy. So nuclear fission is a nuclear reaction in which the nucleus of an atom is bombarded with low energy neutrons. That means this atom, this nuclear atom or heavier atom, it will not dissociate easily. We need to apply some neutron or some radiation with it can be very low energy. However, when this initiator, when this reaction initiates by something, then it can dissociate to give multiple products. So that is called as, here you can see, nuclear reaction in which the nucleus of an atom is bombarded. So I can go for here. So nuclear fission is a nuclear reaction in which nucleus of an atom, only one atom, is bombarded with low energy neutrons, which splits the nucleus into a smaller nuclei. So it splits more than one into a smaller nucleus. That means we have 100. So if we want to dissociate the 100 this number, then either 40, 60, 50, 50 or 30, 70 or like this. These types of smaller nuclei will be produced by the nuclear fission. And for fusion, two or more particles or two or more atoms or nucleus combine to give a new heavier particles. That is very simple. So you can easily understand fusion and fission. Okay, advantage, and if we missed anything, okay, no. Okay, advantage and disadvantage of nuclear energy. All of us already we have learned what are the uses of nuclear radiation or nuclear isotope. So we know the advantages. So no greenhouse gas emission. greenhouse gas, carbon dioxide. So if we use the nuclear power plant, from that process we will not have any carbon dioxide gas, or one of the most important greenhouse gas is moisture. But actually we cannot control the level of moisture in the universe, so we do not consider that moisture or water vapor is the culprit. But actually it has the amount of moisture or water vapor in the universe is huge, so it absorbs huge amount of light or energy. So the most culprit thing is the water vapor. Then we have carbon dioxide, methane. So we cannot control the moisture, so we do not consider about that. That means if we want to fight, if Bangladesh want to fight with America, that may be just out of imagination. We cannot do that. So similarly, we cannot control the water vapor, so we are ignoring this term. But actually the greenhouse gas, methane, carbon dioxide, and the water vapor, these are the also greenhouse gases. So but the one of the most important application uses or advantage of using the radioactive isotopes for the generation of power, that we do not create any greenhouse gases from this. Reliable and steady source of power with modern design. Actually this is the important term we have to include or we have to consider, because reliable and steady source of power, when we can generate or when we can create a power source from the nuclear power plant, if you provide the fuel, then it will never stop. As long as you can supply the fuel, then you can maintain the everything. So with modern design, actually it has been mentioned to make understand that everything is well organized. So you should maintain, or we should maintain the system as scientifically and very accurately. That is modern design. So reliable and steady source of power. But in case of water electricity or hydroelectricity, if the flow of water is reduced and the flow of water or level of water is out of control, out of our control, so we cannot do this. So when we want to get the energy from the our hydroelectricity or the water, in that case sometimes the level of water can be very high, sometimes the level of water can be very low. In that case we cannot control the generation of electricity very often. But reliable and steady source of power as a nuclear power plant, if you supply the fuel, then you can always get continuously, no, as much as fuel you are giving, then you can get the same amount of energy every time. Relative abundance of fuel, okay, that is one thing. Relative abundance of fuel, that means in the universe still we have quite huge amount of uranium. So passive stability and simplicity of latest designs. So passive stability and simplicity of latest design. So we don't need to have very sophisticated design for this process. If you have some time, maybe you can visit the nuclear power plant what we are going to establish at the, maybe it is going to establish in Pabna, is it? So you can have a time to visit there, and those who have visited, who are from other country, then you can have also visit, if you have in your country, or even you can visit the Bangladeshi power plant. So you will see that some big construction made of very big house with very thicker wall, so that the radioactive material cannot be passed through this, or it cannot go very far away. So that is some shielding, very big cover. So we have mentioned some term isolated. That means that is also something which is very isolated from the locality, or very no people will live beside this. Just if we can make quite very thicker wall, some very thicker walls, then these types of radiation can be controlled, and we need to flow some cooling system. We need to have some cooling system, so that the ultimately the design and the processing that are not so complicated. Therefore, the people can use it, the passive stability and simplicity of the latest design. And some disadvantages: generation of radioactive byproducts. So some of the products which are generated after the uses of radioactive materials, so radioactive decay, we are producing some byproducts which are also radioactive. So in that case, if we want to use that types of system, then we need to reduce the radioactivity of the byproducts, or we need to treat them before come into contact with the general people or to the human. Need to decomposition radioactive old reactors. That means those reactors who had 50 years or 30-40 years older design, that time people didn't have very good idea how we can use. So the stations or reactors which has been generated or which has been created 30 or 40 years before, that design need to be decomposed or need to be shut down. Possible catastrophic failure: suddenly if we have some problem, that means the reactions or the systems or the cooling system, if anything is out of our control, in that case we can have some disaster. Like as we can have some example, we will see that some disaster problem with nuclear energy, Chernobyl, that is in Russia, is it? Chernobyl, that was the deadliest or the most dangerous nuclear power plant destruction. And Fukushima in Japan, so here you can see the nuclear accident, radiation continues to leak from Swift plant 3 Mile Island. So these are some examples that has been the nuclear power plant which was out of control, and there was very big danger, and many people have to die. Many people already died. And also something that till now, if the systems, if the nuclear power plants are out of control, then still they can have some radioactive materials continuously generating, and no people can live around this. So that is very big issue. So we need to think about, and if we want to generate any nuclear power plant, the controlling system, I'm not sure how about my country will do that. Some Russian people are working to develop the nuclear power plant, but after they go back, we need to handle by ourselves. So we need to be trained so very well, or also the knowledge. We should have the scientific knowledge how the nuclear power plant works and how to monitor, how to control the system efficiently. So we need to learn that. So hope we will do that. We can do that. Then effects of radioactivity. So when you can see this is the DNA, is it double strand DNA? So when the radioactive element is this is radioactive ray or particle. So when it is coming to our cell, so that is in our cell, that can be good cell or bad cell, whatever. So if it come into contact to our good cell or bad cell, that means the cancer cell or our body cell, normal body cell. So when it come into contact with the body cell or the cell, then the DNA, you can see this is the DNA, it is destroyed. So when the DNA is destroyed, the cell will no longer active. So that cell will be the cancer cell if we have the cancer cell or any other body cell. So if the DNA is not available or the DNA is destroyed, in that case the growth of the cell will be restricted, so that our, if we have the cancer cell, then our cancer cell will be destroyed, so that just we need to specify in which region we have the cancer. That means the cancer cell, just we need to apply the radiation along the region, so that we can damage the DNA of the cancer cell, so that the growth of the cancer cell can be stopped, or completely the DNA is damaged, so the growth can be stopped and no more cancer cell can be created. Therefore we can survive. And then here you can see the effect of radioactivity. What we have seen, that this is huge amount of fire, or it can have huge radiation. So no people around the radioactive plant can live or should not live, because if there is any accident by chance, then that would be very dangerous to the people who are living beside this. And then we can have, now we are going to learn about something, the chemical equilibrium constant. In last class we have learned about the chemical kinetics, and now we are going to learn about the equilibrium constant. Before learning equilibrium constant, we have to learn about the reversible reaction. So what is reversible reaction? Most of the time we consider the reaction is a single directed reaction. That means when we want to generate water, hydrogen gas, 1 mole of hydrogen gas reacting to half mole of oxygen gas to produce 1 mole of water. That is single directed reaction. At the same time it is releasing some energy. So if the reaction can proceed in both ways, that means forward and reverse, that is known as the reversible reaction. Some of the reactions we can have, that means some of the reactions can proceed only in one direction, some of the reaction can proceed in both directions. So when we are having the reaction just in both forward and reverse way, that types of reaction is considered as reversible reaction. And at equilibrium, actually what is equilibrium? Let us consider we have this reaction, N2O4 is forming 2NO2. So at the beginning of the reaction we do not have any product. That means the concentration or number of moles of N2O4 is very high. So if we try to draw, if I have any graph, no. Okay, so just I'm trying to draw a graph here. So let us consider, first I can draw the axis using this line. So this is my x-axis, this is my y-axis. So if we want to have a reaction, that means this one, at the beginning we can have the concentration of N2O4 is very high, or that much, let us consider. So this is our reaction progress, this is x-axis, reaction progress of time, we can consider this is time, and this is the concentration or number of moles, whatever. So when we are starting at the left side, N2O4, in that case we can have that N2O4 is maximum. So as time goes, the number of moles of N2O4, the concentration of N2O4 is going to decrease. So we can have the, if we go for the concentration versus time graph for N2O4, that means we can consider that the number of moles or the concentration of N2O4 is decreasing with time. Now you can easily understand that at the beginning or at the time 0, we didn't have any NO2. That means no number of moles of NO2 or the concentration of NO2 was 0. Then at the time when it was maximum, that time it was nothing. So we will start from 0. Now as time goes, this N2O4 is converting into 2NO2. That means the number of moles of NO2 or the concentration of NO2 is increasing with time as this one is converting into NO2. So we can consider that is, so it is increasing with time like this, and then this one. So at a certain period of time, you can see as we increase, or if we go for longer time period, then we can see that the concentration for this reactant will decrease and concentration for this product will increase. So at a time we can see that both the concentration for the reactant and the product will be same. Actually, we should use another term, not the concentration, the rate. Rate means at the beginning, the rate of the forward reaction was very high because the concentration of this N2O4 was very large, and at the beginning there was no concentration. That means the rate of this reaction. So this reaction was very low. So when the number of moles of N2O4 increases, the rate of dissociation, that means the reverse reaction will increase. That means this NO2 will try to dissociate to form again N2O4. So at the beginning, the rate of the reverse reaction, this is our reverse reaction, this is our forward reaction. So at the beginning, the rate of the reverse reaction is 0, and then with time, the rate of the reverse reaction is increasing and the rate of the forward reaction is decreasing. And at a certain period of time, both the rate of forward reaction and the reverse reaction will be equal, and that is called as chemical equilibrium. That means the time when the rate of forward reaction and the rate of reverse reaction for a reversible reaction is equal, that is called as chemical equilibrium. And at the equilibrium, already have mentioned, at the equilibrium, rate of forward reaction equal rate of reverse reaction. Actually, what does it mean? Sometimes you may think, so the rate of forward reaction and rate of reverse reaction are equal. That means at a certain period of time, graphically, it may be considered the reaction is dead. Actually, that is not, because how many moles of N2O4 is producing to NO2? Exactly same number of moles, the concentration of NO2 is decreasing to form N2O4. So if 5 moles are dissociated to form 5 moles are changing into NO2, then same 5 moles are converted into N2O4. So the concentration or the rate of the reaction remain unchanged during the chemical equilibrium. Now, what is the equilibrium constant? Equilibrium constant is the, if we consider this is our equilibrium, that means at this position, if the reaction proceeds at this position, that means the rate of forward reaction and rate of reverse reaction is same. So now we can consider, in the last class we have learned about the rate of forward reaction, or the kinetics. We have mentioned that the rate of reaction is directly proportional to the concentration of the reactant. So if we consider for this reaction, in that case the rate of forward reaction would be, we can consider the rate of forward reaction would be rate of forward reaction proportional to K multiplied by concentration of N2O4. Again, if we now consider this reaction, that means the NO2 converting to N2O4, that is our forward reaction. Then we can consider the rate of this reaction is NO2K multiplied by NO2 power 2, because the coefficient is 2. So we are giving, so let us consider we are representing the, this is forward part, this is reverse part. So the K of forward equal, that means what I have mentioned, the K multiplied by the concentration of the N2O4, this is, and then for the reverse reaction, the K reverse multiplied by the NO2 power 2. So at the equilibrium, we have defined that the rate of forward reaction and the rate of reverse reaction are equal. So we can write down the rate of forward reaction equal rate of reverse reaction. So from here, we can have that this is a constant term, this is constant term. So we are keeping the constant term in same side, and then rate of K of forward reaction divided by K reverse reaction equal concentration of the products. This is power, whatever we have the coefficient. So concentration of the product power raised to the power and the concentration of the reactants. And as these are two different constants, so the ratio of these two constants will be another constant. We can write down is another constant K. So ultimately we are writing this is our equilibrium constant. So equilibrium constant can be expressed by this way or these types of equation, where we can write down equilibrium constant K equal multiplication of the concentration of the products. As we have only one product, so we don't need to multiply. Or if we had multiple products, then we could write down the equilibrium constant equal the multiplication of the concentration of the products divided by the multiplication of the concentration of the reactants at equilibrium. So that is the equilibrium constant. So the ratio of constants give rise to a new constant, already mentioned, equilibrium constant. The magnitude of K is an indicator of how far a reaction proceeds toward products at a particular temperature. Actually, if the value of the K from this equation, you can easily understand, if the value of K is a very large number, then what you can understand from this? If the value of K is a very large number, if we consider, if the value of K is a very large number, that means this ratio is also a very large number. Is it?
Yeah, then the forward reaction is more.
Yes, exactly. That means the magnitude of K is an indicator of how far a reaction proceeds toward products at a particular temperature. That means how far the reaction will move to the right. If the value of K is very large, in that case, the more forward reaction will proceed and that will produce more products. And if the value of K is very less or very short, in that case, we can consider the dissociation or the formation of product will be very less. As long as the reactant produce some product, suddenly the product dissociates to product recombines to form the reactant. That means the forward reaction is neglected in that case if the value of the K is very small. So we can consider this is the ratio. So if the value of K is very large, the concentration of NO2 will be very large, or if the K is very less, then concentration of this one would be very more. Okay, so the magnitude of K is indicator of how far the reaction proceeds toward products at a particular temperature. Okay, then we have general expression of K. Just as I have mentioned already, if we have multiple reactants and multiple products, we have here A is the reactant, A is the coefficient, B is the reactant, and B is the coefficient, C is the product, C is the product, C is the coefficient, D is the product, and D is the coefficient. So ultimately we can write down the value of Kc or equilibrium constant equal the multiplication of the concentration of the products. Here you can see the concentration of the two different products C and D power to their coefficient, power raised to as their coefficient. So the coefficient for C is C and coefficient for D is D. So this is the multiplication of the concentration of the products divided by the multiplication of the concentration of the reactants. So that is very simple. This is if the reactants and products are in terms of liquid or solid. Actually, in terms of solid, we don't need to have, but in terms of liquid, if the concentration, in terms of if the concentration is known, we can use to find out the value of Kc or equilibrium constant using this formula. But if we have all the reactants or some of the reactants and products are in gaseous form, in that case, we cannot use the concentration term. In that case, it is better to use the partial pressure. That means how many components? This is one component, this is another component, this is another component, this is another component. So in the system, we will have 4 different components, 2 reactants, 2 products. So if we have 4 different components or of gas in same container, so every component will give some partial pressure to the system or the container. Therefore, we can use the partial pressure in terms of concentration. Here, if the samples are, that means reactants and products are in liquid state, then we can have the concentration term. But if the reactants and products are in gaseous form, then we cannot use the term concentration. So in that case, we can use the partial pressure, which is ultimately the representation of concentration. That means how many particles are there. If the number of particles in the container of one component is very high, therefore the partial pressure of that component will be very high. So we can easily understand that the partial pressure can be directly related to the concentration. So we can use the partial pressure to express the equilibrium constant for the gaseous reactants and products. So that is also similar what we have written here. We have mentioned concentration of the reactant product, concentration of the product power C, concentration of product D power D. Similarly here, partial pressure of C, that means the product power C, partial pressure of D power D, partial pressure of A power A, partial pressure of B power B. So that these both are exactly similar, except these are in liquid state and these are in gaseous form, because in the gaseous form we cannot have the value for the equilibrium, we cannot have the concentration value. So another term, actually we know the value of ideal gas equation. Ideal gas equation PV equal nRT, we know. So if we know the value of PV equal nRT, so using this equation, we can create a relation between the Kc and Kp. So that is the relation between Kp and Kc. Kp equal Kc into RT delta N of gas. So for any system, if we have some gaseous form, then if we can find out the value of Kp, then using this law, we can have the value of Kc also. Here, R is the molar gas constant, T is the absolute temperature or Kelvin temperature. So T is the Kelvin temperature, that means the temperature at which the reaction is happening, and then delta N. Delta N is the difference between the number of number of moles of products minus the number of moles of reactants. So if we have we have to find out the coefficient for this, the C plus D minus A plus B. So delta N is the difference of the number of moles between products and reactants. So to find out the value of N, we will use the delta N equal C plus D minus A plus B. So this is the formula or the relation between Kp and Kc. So using these types of formula, we can have this Kp equal Kc RT into RT delta N of gas. So from here, we can have the idea, if we have the reactants liquid or gas, we can have the equilibrium constant, and if we know one, then we can go for another one using this types of formula. Okay, then relationship to the of K of balanced reaction. Okay, so reverse the reaction, invert the value of K. Already we have mentioned that one in some other case. So reverse the reaction, invert the value of K. That means if we have the reaction, hydrogen and oxygen is reacting to form water. Here you can see hydrogen gas and oxygen gas is reacting to form water. At the same time, it is generating some energy. So if we reverse the reaction, that means this is kind of forward reaction. So the value of K for this reaction is 1.4 into 10 to the power 83 at 298 Kelvin. That means 25 degrees Celsius. So at this temperature, the rate of this forward reaction, that means that this is the value of K actually. That means the forward reaction, as already we have mentioned in the previous slide, that means the value of K determines, here you can see the magnitude of K is an indicator of how far a reaction proceeds toward the products at a particular temperature. As already I have mentioned, the value of K, if the value of K is very large, in that case we can have the idea that NO2, that means the product concentration, the concentration of product is very high. So the reaction can be considered as forward reaction. So as already I have mentioned in for the here for this reaction, the value of equilibrium constant is 1.4 into 10 to the power 83. That is a huge large number. Therefore, that reaction is undoubtedly considered as the forward reaction. That means it is very difficult to dissociate this water molecule. So this reaction mostly considered as forward reaction. Now, if we want to reverse this reaction, the reverse reaction, invert the value of K. That means you have to invert the value of K. That means 1 over 1.4 into 10 to the power. That means if we want to find out the value of K for the reverse reaction of this, that means how the dissociation of water, H2O dissociates to give hydrogen and oxygen. The value of K will have like this way, 1 over 1.4 multiplied by 10 to the power 83. That is the value of K if we want to reverse this reaction, and then multiply the coefficient by a common factor. But multiply the coefficient by a common factor, raise the equilibrium constant to the corresponding power. Okay, what does it mean? Multiply the coefficient by a common factor, raised to the equilibrium constant to the corresponding power. That means if the reaction was half, if we had only 1 mole, if we had 1 mole, here half mole, here we are having 1 mole, in that case we are multiplying with 1 by 2 or 0.5, actually 1 by 2 we can consider, multiply the coefficient by a common factor, raise the equilibrium constant to the corresponding power. So this is our equilibrium constant. In that case we have to, as we are multiplying with 1 by 2, that will also come as 1 by 2. We are using the coefficient 1 by 2 here. The power would be, that means the equilibrium constant should be as a power, as we are using the coefficient. What is the multiplying factor? So ultimately it should be a square root. That means if we want to remove this half, that is becoming a square root. So the multiplying, whatever the coefficient we are multiplying, that would be the power to the rate constant. Then divide the equation by a common factor corresponding root. As already I have mentioned this one, actually we have used the half as the multiplying factor. So divide the equation by a common factor corresponding root. Divide the equation by a common factor corresponding root, as already I have mentioned, that is a square root. We have divided by 2, so we are having the square root. And then the value of k 10 to the power 10, a reaction going to completion. That means if you have the value of equilibrium constant value 10 to the power 10 or more, that means the value of k, if the value is more than 10 to the power 10 per second, actually the k is always with time. So the value of k can be mole per second, like this. So the rate, if the value of k is more than 10 to the power 10, the reaction is going to completion. That means no reactant will be there. Almost all the reactant will be converted into products. And if the value of k is 10, here you can see for this one, or which one? Okay, this one. This one, the value of k is very large. So 10 to the power 83, which is very far away from 10 to the power 10. That means the reaction goes to completion. And if the value of k is less than 10 to the power minus 10, then, or even smaller than this, then a reaction not occurring in the forward direction. So in that case, the reaction do not proceed at all in the forward direction. It proceeds reverse way. That means as long as the reactant making the product dissociating to give the reactant again. So the reverse reaction is very fast. So here we can see that the value of k is 1.9 into 10 to the power minus 23. Actually, this is the reaction I have shown many times. That means calcium carbonate. Normally, we are using the calcium carbonate to build the building or some constructive work. So if it could dissociate, like if it could have the value of k like this one, then we could not make the building. And the rate of dissociation of calcium carbonate is very slow, so that we can have a constructive work, so that we can have the information. So as we can see that the value of k or equilibrium constant is very small, so the calcium carbonate will not decompose very easily. Or ultimately we can see calcium oxide and carbon dioxide, they can easily form the calcium carbonate, not going to the forward direction, even it is going to the reverse reaction. And then hopefully the last slide, the alternating conditions, Le Chatelier's principle. So if we have some equilibrium reaction or the reversible reaction in the chemical equilibrium, that means we have drawn the at a certain period of time, the rate of forward reaction and the rate of reverse reaction becomes equal. That is the chemical equilibrium, and we have find out the value of chemical equilibrium constant. Now if we want to shift, if we want to change the equilibrium position in a certain direction, then we have to apply some factor or the parameters that are considered as concentration, temperature, pressure, and catalyst. Actually, the equilibrium, at the equilibrium, the catalyst has no effect. Just we can first we start from the concentration. If we have a reaction like this and the reaction is in equilibrium, and we want to have, this is the process by which the ammonia is produced, and ammonia production can be more, it can help to produce more amount of urea fertilizer. So to produce more urea fertilizer, we need more ammonia, and the reaction is reversible. So if the reaction is reversible, then we cannot get more ammonia. So we have to use, in certain condition so that we can get more amount of ammonia. That means we can shift the equilibrium towards right. That means if we can apply some certain parameters so that the equilibrium position can be shifted towards right, that can give us more amount of ammonia. So here you can see if the reaction is reversible reaction, at the same time we can see the reaction is an exothermic reaction. So for these types of reaction, just let us ignore this term first, because we are considering only the concentration term. Just let us ignore this part. So if we increase the concentration of any of the reactant, either nitrogen or hydrogen, in that case, if we add more nitrogen, so that more nitrogen will react more hydrogen. So that can have more ammonia production. That means if we can increase the concentration of the reactant, then we can proceed the chemical equilibrium towards right, which can help to make more amount of ammonia. Again, if we mention that if we increase the concentration of ammonia in the right side, in that case, we can see that more ammonia will decompose to form nitrogen and hydrogen. That means if we increase the concentration of the product, then our reaction equilibrium or the chemical equilibrium will move towards left. So more amount of ammonia or the more amount of products will be dissociated to form the reactant. That means the equilibrium position will move towards left. So the term for the concentration are done. So if we increase the concentration for the reactant, the equilibrium position will move towards right, and if we increase the concentration of the product, then equilibrium will move to left. Again, if we go for the decrease, if we decrease the concentration of nitrogen or hydrogen, that means if we decrease the concentration of the reactant, then the equilibrium will move to left. And if we decrease the concentration of this, then equilibrium will move to right. Now change in pressure and volume. So actually pressure and volume both are directly related. Sorry. If we change the concentration, sorry, if we increase the volume, so if we increase the volume, the pressure decreases. If we decrease the volume, pressure increases. So just we can monitor or we can explain just one of them. We don't need to consider both of them. So just we can increase the pressure or decrease the pressure by changing the volume. So now if we have these types of reaction, so by changing the pressure of this reaction or the system, we can have or we can move the equilibrium in certain direction depending on how much pressure if we are increasing or decreasing. So the formula or the idea for this process is that if we increase the pressure of this reaction, just remember this, if we increase the pressure, the equilibrium position will move towards that direction in which the number of moles is less. That means in this reaction, we can see the number of moles for this left side is 1 plus 3, 4 moles, and the product is 2 moles. Therefore, we are having, if we increase the pressure, in that case, we can have the equilibrium position can be moved towards right. Therefore, for this reaction, if we want to generate more ammonia, then we can increase more pressure to this. Then temperature. For the temperature need to be considered, we have to think about if the reaction is exothermic or endothermic. If the reaction is exothermic, then what means? It means that the number of mole when the reaction proceeds in the forward direction, it produces this mass energy ultimately. So if the reaction is exothermic, then when 1 mole of nitrogen and 3 mole of hydrogen is producing 2 mole of ammonia, we are getting 92 kilojoule mole per 90 kilojoule mole of energy, which is helping to dissociate this ammonia. So that if we increase the temperature for this reaction, more amount of energy will be released. So we should go for the lower temperature for this reaction if we want to get more amount of ammonia. But that is also complicated at very lower temperature. The rate of the reaction is very slow. So you may get the percentage of yield for ammonia is high, but the rate is very slow. So you cannot use very low temperature. So we need to use some optimum temperature or optimum condition. So if we want to generate the more amount of ammonia, that means this ammonia will be used to produce urea fertilizer. So if we want to more ammonia, then we have to use or we have to prepare more amount of ammonia, so that we need to use certain condition that more ammonia can be produced. So that is considered as optimum condition, and optimum condition is for this reaction, if we consider 200 atmosphere pressure. That means we have mentioned that if we can increase the pressure for this reaction, we can get more ammonia, and if we can have more temperature, at low temperature the percentage of yield is very high, but at low temperature the rate of the reaction is very slow. So we can increase the temperature around 450. At this temperature the rate of the reaction is quite fast and the percentage of yield is not very low. And catalyst, actually for the reaction to make faster or slower, or to alter the rate of the reaction, we can use a catalyst. But the problem is that if we use a catalyst for a reversible reaction at chemical equilibrium, actually it do not help anyway. It do not change the position of the chemical equilibrium, because once the reaction is in equilibrium, the catalyst increases the rate of forward reaction, and also same time it increases the rate of reverse reaction. That means just it is how many moles of reactant will produce to product convert into product, or how many moles of product will convert into reactant, just it increases, but the position of the equilibrium do not change. So the catalyst has no effect on the equilibrium condition or equilibrium position, but it can help if you start the reaction at the beginning. It can help to get the chemical equilibrium faster, because a catalyst can help to increase the rate of the forward reaction, and also at the same time, as the more number of products are forming, so more products will dissociate into more reactants. So we can gain the equilibrium faster when we use catalyst, but if we do not use catalyst, it can take longer time. Okay, so I think you have any question? I cannot hear you. Okay, so we are done. Thank you very much. And now I'm stopping sharing. And where is my recording? Stop.